Good morning, all of you. I'm going to start that this session. In this session, I discussed about regenerative cycle with two feed water heater. I have stopped it here only because of the interrupt. I have stopped it. Okay, once again, I can explain it. This two feed water heater. Okay, here in the two feed water, it will be contains two heaters, heater one and heater two. Here in the heater one, M1 amount of steam which will be trapped. In the heater two, M2 amount of heat will be trapped it here. Then here boiler, which we are supplying heat to the boiler, it will be produces a superheated steam here at stage 2, 1 kg of steam which will be passed it to the turbine. Here the expansion process will be taken place. During the expansion process at stage 3, M1 amount of steam which will be trapped and it will be entering into the heater 1. Then at stage 4, M2 amount of steam which will be trapped, then it will be entering into the heater 2. The remaining 1 minus M1 minus M2 amount of expanded steam which will be passed to at stage 5 to the condenser. Here the condensed fluid once again pumped to the heater 2. Here 1 minus M1 minus M2 amount of condensed fluid which will be at stage 7, it will be entering into the heater 2. Here in the heater 2 it will be contains M2 amount 1 minus M1 minus M2 plus this is M2 M2 and it will be cancelled. The remaining fluid 1 minus M1 amount at stage 8 which will be pumped to the heater 1 here. That is a 1 minus M1 condensed fluid. Once again it will be entering into the heater 1 at stage 3. M1 which will be entering and M1 which will be cancelled. Then 1 kg of condensed liquid either fluid which will be entering into the boiler. Okay, this cycle which will be repeats here. Okay, this is the working principle behind two feed water heater. Okay, this is what TS and HS diagram here. That is a stage 1 to 2, that is a superheated steam which will be obtained. At 2 to 3, that is M1 amount of steam which will be trapped, and at stage 4, M2 amount of steam which will be trapped. At the stage 5, M1 minus M1 minus M2 amount of steam which will be trapped. Okay, such a way that we have to write down all this TS and HS diagram. Then we have to write down the efficiency expression. Okay, efficiency is equal to W net divided by QS. W net you can calculate it by WT minus WP. WT turbine work, that is 1 kg into 1 into H2 minus H3 plus 1 minus M1 into H3 minus H4 plus 1 minus M1 minus M2 into H4 minus H5. Then I have to write down 1 into H3 minus H2 minus H3, then 1 minus M1 into H3 minus H4, then 1 minus M1 minus M2, that is what? H4 minus H5, H4 minus H5. Then WP is equal to pump work, 1 minus M1 minus M2, H7 minus H6, H7 minus H7 minus H6, then 1 minus M1 into H9 minus H8 plus 1 into H1 minus H10. Then heat supplied, that is what? H2 minus H1 QR. Heat rejected is equal to 1 minus M1 minus M2, that is what? H5 minus H6. Okay, heater, then we have to take into concentrate on heater 1 and heater 2. Heat lost is equal to heat gained. Okay, loss, inlet condition is equal to outlet condition, that's all. Okay, now I'll write down here with respect to M1 into H3 at heater 1, M1 into H3 stage plus 1 minus M1 into H9. These are the M1, this is you can call it the H3. Okay, this is 1 minus M1 into H9. These are the inlet condition is equal to the outlet condition 1 into H10, 1 into H10. Okay, that is what I have written it here. Then we have to calculate mass of M1. It should be calculated by M1 is equal to H10 minus H9 divided by H3 minus H9. Okay, similar way we have to write down for the two feed water heater. Second feed water heater, inlet condition is equal to the outlet condition, that is why M2 into H4. These are the M2 into H4 and H7, 1 minus M1 minus M2 into H7. These are the inlet condition. Then is equal to outlet condition 1 minus M1 into 1 minus M1 into H8. This is the outlet condition. Then based on this relationship, you have to find out the value of M2. M2 is equal to 1 minus M1 into H8 minus H7 divided by H4 minus H7. This is the value of M1. This is the value of M2. Mass of M1 and mass of M2 we have to calculate it. This is the expression, efficiency expression. Then The last the theory aspects of vapor power cycle is binary vapor power cycle. Okay, binary, that the name indicates here the two cycles. Okay, it will be existing here, it will be placed in the series. Okay, one cycle it will be rejected heat, it will be utilized for the another one cycle, in such a way that the working principle behind this binary vapor power cycle. Okay, this is what the black diagram of binary vapor power cycle. Okay, this is what the first cycle you can call the mercury cycle. This is, you can call it the mercury cycle. The mercury cycle, which will be consist of a mercury boiler and mercury turbine and mercury condenser. Then this condensed mercury once again pump up to the boiler. This is what the one cycle. Okay, this mercury condenser, it will be leaving the heat. Okay, it will be the heat rejection process will be taken, rejected the heat once again, that will be passed to the pass it to the superheater. In the superheater, it will be produces a steam here. That steam once again pass it to the steam turbine. Okay, here the steam turbine, the expansion process will be taken place in the 1 to 2. Then condensed that expanded steam once again pass it to the condenser. 2 to 3, the condensation process will be taken place. Condensed fluid once again pump up to the economizer. In the economizer, once again the hot gases through a economizer, hot gases to the atmosphere. Then the condensed steam once again pass it to the condensed steam once again fluid, which once again pass it to the here the mercury condenser. Here in the mercury condenser, the mercury feed pump, through a feed pump, which will be entering into the mercury boiler. Okay, lies that the working principle behind this mercury binary vapor power cycles are working. Okay, that's mercury boiler. Another one is a steam turbine, it will be coupled to each other in a series. Okay, then the working principle behind this binary vapor power cycle. In the mercury cycle, we are using a one chemical component, that is what mercury diphenyl ether, other you can correct the sodium are used along with the steam. Okay, then once again I can explain it here. The mercury boiler, in the mercury boiler we are supplying heat to the mercury boiler, it will be produces a mercury steam. Then it will be passed to the turbine here, mercury turbine, the expansion process will be taken place A to B. Then condensed the mercury fluid, it will be expanded mercury steam, which will pass it to the mercury condenser. Here the condensation process will be taken place. Condensed mercury fluid we once again feed to the boiler through a pump. Then during the condensation process in the mercury condenser, that heat is leaving from the mercury condenser. That heat once again at stage 6 once again pass it to the superheater. Here in the superheater, it will be produces a steam here. That steam once again passes to the stage 1 to the turbine, steam turbine. Here the expansion process will be taken place. The expanded steam once again passes to the condenser. The condensation process will be taken place at condensed fluid. That is a fluid once again passes to the pump to the economizer. Through a economizer, it will be heat is leaving to the atmosphere. That is a condensed fluid once again passes to the mercury condenser, this mercury condenser. Then the mercury feed pump, through a feed pump, once again it will pass it to the mercury boiler. Okay, in this way that cycle it will be working principle behind this binary vapor power cycle. This is what the TS diagram. This is first the initial diagram is mercury cycle, then lower diagram is a steam cycle. Okay, now we will be having a simple expression is there here. Mercury cycle expression, mercury cycle efficiency is equal to Q1 minus Q2 divided by Q1. It becomes cross multiplication. Mercury cycle into Q1 is equal to Q1 minus Q2. Here you can take a common term of Q2. Here it becomes Q1 minus efficiency of mercury into Q1. Q2 is equal to, you can take a common term of Q1 here, it becomes 1 minus mercury cycle. Okay, similar way for a steam turbine, efficiency of the steam turbine is equal to Q2 minus Q3 divided by Q2. That is what 1 minus Q3 divided by Q2. It becomes efficiency of the turbine into Q2 is equal to Q2 minus Q3. Here Q3 is equal to Q2 minus efficiency of steam turbine into Q2. Q3 is equal to Q2. You can take a common term here, 1 minus efficiency of the steam turbine. Okay. Now efficiency is equal to efficiency of the binary cycle is equal to efficiency is equal to Q3 divided by Q1. Q3 can calculate Q1 minus Q3 divided by Q1. It becomes 1 minus Q3 divided by Q1. Instead of Q3, can substitute Q2 into 1 minus efficiency of the steam turbine divided by Q1, Q1 it will be Q2. Then that instead of Q2 I can write down here Q2 is equal to Q1 into 1 minus mercury cycle. That is what Q1 into 1 minus mercury cycle divided by Q1, 1 minus efficiency of the steam turbine. Q1 and Q1 it will be cancelled. Then remaining term 1 minus mercury cycle efficiency into 1 minus steam turbine efficiency. Then we have to get this expression of efficiency, mercury cycle efficiency plus steam turbine efficiency minus mercury cycle efficiency into steam turbine efficiency. This is all about the theory aspects come across in the module 3, that is what vapor power cycle. Okay, now we can solve a few problems on vapor power cycle. Now I can read out the problem here. Steam enters a steam turbine using reheat cycle at 150 bar 350 degrees centigrade. The reheat pressure is 25 bar and exhaust pressure is 0.05 bar. The temperature of reheat steam is 300 degree centigrade. Calculate the cycle efficiency and power developed for a steam flow rate of 3000 kg per hour. Condenser, the pump. Consider the pump work. Okay, this is also one of the examination problem. Okay, here the reheat cycle is there, so that's why we have to write down that reheat cycle TS and HS diagram. Here 1 to 2, that is condensed heat, it becomes a liquid wet steam. It's okay, 1 to 2 it becomes within that curve. You should like that only, you should write down within that curve. Then we have to write down from the molar chart, we have to write down the values of H1, H2 and H3 and H4. Okay, H1 is equal to 2720.4 kg kilojoules per kg. Then H2 is equal to 2410 kilojoules per kg. H3 is equal to 3010 kilojoules per kg. H4 is equal to 2040 kilojoules per kg. X4 drainage fraction is equal to 0.78. Then at pressure P3 is equal to 0.05 bar. Then VF, okay, specific volume at the fluid condition at saturated fluid is equal to 0.0010 meter cube per kg. HF is equal to 137.8 kilojoules per kg. HF is also equal to HF5. Okay, then efficiency of the thermal efficiency is equal to WT minus WP divided by heat supply. WT is equal to H1 minus H2 plus H3 minus H4. It becomes 1280 kilojoules per kg. Pump work is equal to VF into P1 minus P3. That is, the P1 is 150 minus 0.05 into 0.0010 into 10 to the power of 2. That is, it becomes 15 kilojoules per kg. That is, the QS is equal to H1 minus H6 plus H3 minus H2. QS values become 3537.2 kilojoules per kg. Then thermal efficiency is equal to 1280 minus 15 divided by 3537.2. It becomes 35.76. Power is equal to M into WT minus WP. It becomes 1054.17 kilowatt. Okay, this is a simple problem on reheat cycle. Okay, this is also a very similar problem on what I have discussed in the earlier. Okay, the same problem which will be existing here also. An ideal Rankine cycle with the reheat is designed to operate according to the following specifications. Pressure of steam at high pressure inlet is equal to 20 megapascal. Temperature of steam at a high pressure turbine is 550 degrees centigrade. Temperature at the end of reheat is equal to 550 degrees centigrade. Pressure of steam at the turbine exhaust is equal to 15 kilopascal. Quality of steam at turbine exhaust is equal to 90%. Determine pressure of steam in reheater, ratio of pump work to turbine work, ratio of heat rejection to the heat addition, cycle thermal efficiency. This is one of the examination problem also. We have to write down that reheat cycle. Okay, then 1 to 2, that is it becomes wet steam. So that's why within that curve we should write down the here also in the HS diagram at point 2 we have to write down a wet steam. Okay, not dry saturated steam. Dry saturated steam in that point 2 which will be exactly at the curve, but it becomes wet, it becomes 2. We have to within that curve, like that only we should write down the TS and HS diagram. That is very important in the above problem also and this problem also. Okay, then P1 is equal to 20 megapascal, it becomes 200 bar. Then P3 is equal to 15 kilopascal is equal to 0.15 bar. T superheated is equal to T superheated temperature. The temperature it will be remain same. That is a 550 degrees centigrade. It will be reheated into the same temperature. That is a 550 degrees centigrade. X4 drainage fraction is equal to 0.9. From the steam table, we have to write down P3 is equal to 0.15 bar. That is the value of HF is equal to 226 kilojoules per kg. Then VF is equal to 0.0010140 meter cube per kg. From the molar chart, we have to write down this value of H1 is equal to 3400 kilojoules per kg. H2 is equal to 2900 kilojoules per kg. H3 is equal to 3575 kilojoules per kg. H4 is equal to 2365 kilojoules per kg. Okay, these molar chart, how to read the molar chart? Already we know this basic thermodynamics in the semester 3. That is basic thermodynamics in the pure substance. We know this to read how to read this molar chart. Based on that one, you should read the value of H1, H2, and H3 and H4. Then also the pressure value P2 is equal to 35 bar. Then we have to find out the value of WT. Here the high pressure turbine and low pressure turbine is there, the two turbines. Then we have to write down here the work done of turbine. That is what H1 minus H2 plus H3 minus H4. It becomes H1 is equal to 3400 minus H2 is equal to 2900 plus H3 3575 minus 2365. It becomes 1710 kilojoules per kg. Then pump work is equal to VF into P1 minus P3. VF is 0.0010140 into P1, that is what 200 minus 0.15. It becomes 20.27 kilojoules per kg. Then WP is equal to H6 minus H5. H6 minus H5. H6 is equal to 246.27 kilojoules per kg. The ratio of WP divided by WT, it becomes 0.0118. Then heat supplied QS is equal to H1 minus H6. It becomes 3153.73 kilojoules per kg. That heat rejected QR is equal to H4 minus H5. It becomes 2139 kilojoules per kg. The ratio of heat rejected to the heat supplied is equal to 0.678. Then thermal efficiency is equal to WT minus WC divided by heat supplied. That is what WT. It becomes 1710 minus 20.27 divided by 3153.73. It becomes thermal efficiency is equal to 53.58%. Okay, this is all about this expression of the problems on reheat cycle when it becomes wet condition. Okay, this is a very another one important problem. Here just you can observe here what are the difference I am going to tell the last problem and this problem. In a reheat cycle, steam at 500 degrees centigrade expands in high pressure turbine till it is saturated vapor. It is then reheated at a constant pressure to 400 degrees centigrade and then expanded to low pressure turbine to 40 degrees centigrade. If the maximum moisture content at the turbine exhaust is limited to 15%, find the reheat pressure, efficiency, net specific work output, pressure of steam at the inlet to the high pressure turbine. The reheat cycle, the steam at 500 expands in high pressure turbine till the saturated vapor. Then this is very important here. The 1 to 2 is to be exactly meet at the curve. Okay, not at the inside the curve. What I have told in the last problem, it will be the inside the curve is there. That is a 0.2 at 0.2. That is a they are not mentioned it saturated vapor. Here they are mentioned it. It becomes saturated vapor. That is what I have written. It expansion is up to the turbine till it is saturated vapor. Then at 0.2 exactly meet at this curve. Like that only we have to write down this 0.2 in TS and HS diagram. That is very very important in the point of examination also while solving the problems. Okay, then from the problem from the steam table at 40 degrees centigrade, P4 is equal to 0.07375 bar. From molar chart we can read out the value of P4 is equal to 0.07375 bar. X4 dryness fraction is equal to 0.85. H4 is equal to 2220 kilojoules per kg. Then H3 is equal to 3250 kilojoules per kg. H2 is equal to 2800 kilojoules per kg. H1 is equal to 3010 kilojoules per kg. P2 is equal to 20 bar. P1 is equal to 150 bar. Then reheat pressure is equal to P2 is equal to 20 bar. From molar chart, we can read the value of P2. Pressure of steam at the high pressure turbine P1 is equal to 150 bar. From chart you can calculate WT. WT is equal to high pressure and low pressure turbine. That is what H1 minus H2 plus H3 minus H4. It becomes 1540 kilojoules per kg. Then heat supplied, that is a reheat will be taken place here. H1 minus H6 plus H3 minus H2, that is a heat supplied is equal to 3577.9 kilojoules per kg. Then WP is equal to P1 minus P3 into Vf, we can calculate that is a Wp, that is a 15.109 kilojoules per kg. From the steam table at 40 degrees centigrade, that is a value of Hf is equal to 167.5 kilojoules per kg. Vf is 0.010078 meter cube per kg. Then W net is equal to Wt minus Wp. It becomes 1357.39 kilojoules per kg. Then Rankine efficiency is equal to W net divided by QS is become 42.62%. The steam rate 3600 divided by W net, it become 2.36 kg per kilowatt hour. Okay, this is all about the problem on dry saturated, the vapor at superheated steam, they expanded at the saturated vapor. Okay, like that we have to write on the TS and HS diagram. Okay, then okay, we can solve another one problem on gas turbine, Rankine cycle, vapor power cycle. Then this is last problem. I will solve it. The remaining thing you can read out all the problems in my notes. Okay. Then steam at 20 bar 360 degree centigrade is expanded in a steam turbine to 0.08 bar. If then enters a condenser where it is condensed due to saturated liquid water, the pump feeds back the water into the boiler. Assumed the ideal pressure find per kg of steam, the net work and cycle efficiency. If the turbine and pump each have 80% efficiency, find the percentage reduction in net work and cycle efficiency. Here in this problem, there's an ideal cycle and also actual cycle which will be existing. Then what is the percentage reduction change, percentage change which will be existing with respect to the ideal and actual condition we have to write down. Okay, this is what the TS diagram with respect to the ideal condition. Okay, then from the problem, P1 is equal to 20 bar. T superheated temperature is equal to 360 degrees centigrade. P2 is equal to 0.08 bar. Efficiency of the pump and turbine is 0.8. From the steam table, you should note down the value. P1 is equal to 20 bar. T saturated temperature is equal to 212.8 degrees centigrade. Vg1 is equal to 0.09955 meter cube per kg. Hg1 is equal to 2797.37 kilojoules per kg. Sg1 is equal to 6.3377 kilojoules per kg degree Kelvin. At pressure P2 is equal to 0.08 bar. Vf2 is equal to 0.0010084 meter cube per kg. Hf2 is equal to 173.9 kilojoules per kg. Hfg2 is equal to 2403.1 kilojoules per kg. Sf2 is equal to 0.5926 kilojoules per kg degree Kelvin. Sfg2 is equal to 7.637 kilojoules per kg degree Kelvin. Sg2 is equal to 8.2295 kilojoules per kg degree Kelvin. From ideal process, we have to process 1 to 2. S1 is equal to S2. Then P1 is equal to 20 bar. Then T superheated temperature is equal to 360 degrees centigrade. S1 is equal to 6.893 kilojoules per kg degree Kelvin. S2 is equal to SF2 plus X2 into SFG2. Then it becomes X2 value. It becomes 0.821. 8 to 1. Then H1 is equal to 3106.49 kilojoules per kg. H2 is equal to HF2 plus X2 into HFG2. It becomes 2146.85 kilojoules per kg. Then WT is equal to H1 minus H2. It becomes 959.65 kilojoules per kg. Then WP is equal to Vf2 into P1 minus P2. Then you can the 2.01 kilojoules per kg. Heat supplied is equal to H1 minus H4. It becomes H1 minus HF2 plus WP. It becomes 2930.52 kilojoules per kg. W net, WT minus WP. It becomes 957.64 kilojoules per kg. Cycle efficiency is equal to W net divided by heat supplied. It becomes 32.68 with respect to the ideal condition. Similar way, that actual condition is that dotted line, it will be express the actual condition. Here also the actual condition is there. We have to write, we have to calculate once again the efficiency of the cycle. efficiency of the turbine is equal to H1 minus H2 dash divided by H1 minus H2. H2 dash becomes 2338.8 kilojoules per kg. Then pump work is equal to H4 minus H3 divided by H4 dash minus H3. H4 dash is equal to 176.4 kilojoules per kg. Then heat supplied is equal to H1 minus H4 dash is equal to 3106.49 minus 176.4. It becomes HQS is equal to 2930.09 kilojoules per kg. Then WT turbine work is equal to H1 minus H2 that is becomes 767.69 kilojoules per kg. Then WP is equal to H4 dash minus H3. It becomes 2.01 kilojoules per kg. W net is equal to WT minus WP. It becomes 765.68 kilojoules per kg. Then actual efficiency of the cycle, it becomes 26.13. Then reduction in efficiency with respect to the ideal and actual condition, it becomes 32.68 minus 26.113. It becomes 6.55%. The reduction in percentage efficiency is 6.55%. Efficiency reduction will be taken place here. Okay, this is the problem with respect to the actual and ideal condition. Okay, the rest of the problem is which are available in my notes. You can, all of you can refer my notes. Okay, whatever the important thing I have discussed in this class. Thank you one and all.